Okay, let's take these three. All right, I have 3 as the base. We're looking for the exponent in order to get 9. So this one's fairly easy. You're knowing 3 squared is equal to 9. So that one's not bad. Let's take the next one where you have a base of 9 raised to what power is equal to 1/3. Now that might be a little bit more difficult for you to see, but let me show you another way that you could work on this. Let's get both of these two sides of the equality with the same base. So let's break it down as a base of 3, because that would be common for both sides. So let's rewrite 9 as 3 squared. And we're raising that to the x power. I'm going to take 1/3, and I'm going to write that as a base of 3, but it's to the -1 power, because it's actually 1/3. And now we have like bases, therefore the exponents must be equal, and I can write an equation. 2x is equal to -1, x is equal to -1/2. So that might make it a little bit easier for you when you're working on a problem, rather than just trying to think of what would the answer be. You can actually write an equation for it if you have like bases. So let's do the same thing with the next one. We have 1/2 raised to a power is equal to 32. Now again, that might be a little bit more difficult for you to think of what the log or the exponent is. So if I write 1/2 as 2 to the -1, and then I'm raising it to the x power, and I write 32 as a base of 2 to the 5th power. And now I can write an equation that says -x is equal to 5, therefore x is equal to -5. Okay, these 3 might be a little bit easier. You have the base of 5. What is the log or the exponent that you're raising 5 to in order to get 1? So 5 to the 0 power is equal to 1. 3 is your base. 3 to what power is equal to 3 to the 5th. So we have like bases, therefore we equate the exponents, and x must be equal to 5. Now this one has log base 7 of 5 on the right equals log base 7 of x. What is x? Well, x must be 5. It's just filling in that equation. So let's graph a logarithmic function. So we worked on graphing exponential functions. So think of this then as exponential. Your base is 2 raised to the y power, because the log is the exponent, equals x. And if you think of making a table of values, I think it would be easier for you to graph this. Now typically when we make a table of values, we pick our x values and then find y. This time we're going to pick the x values and find the y. Much easier than to work backwards. So let's pick a y value of 0. 2 to the 0 power is 1. Let y be 1. 2 to the first power is 2. Let y be 2. 2 to the second power is 4. Let y be -1. 2 to the -1 power is 1/2. And -2. 2 to the -2 is 1/4. So instead of picking x, we're going to pick y, and then just graph this. So we have the point 1, 0. We have the point 2, 1. We have the point 4, 2. Then we have the point -1. We have the point 1/2, -1. And we have the point 1/4, -2. So what we're getting is a graph that looks like this. Okay, so what we want to look at now is what is the domain and range of a logarithmic function. So you're going to notice that the domain, what you're putting in for your x values, we're going to stay to the right of the y-axis and not including 0. So we're going to go from 0 to infinity for the domain of a logarithmic function. The range that you're going to get, as you can see up and down, you're going from negative infinity to infinity. So we need to start looking at what is the domain and range of logarithmic functions. The domain has to stay greater than 0. The range can be from negative infinity to infinity. So let's take a look at some problems. Okay, so when we look at log base 3 and we get of 2 minus x, we have to keep 2 minus x greater than 0. So we have negative x is greater than negative 2, so x is less than 2. So we're keeping here the domain because we're keeping our log as being greater than 0. Then we can put in from negative infinity to 2 as the domain. Now I'm going to put the base in here of 10. Typically we don't do that, but I'm going to put it in here for this particular problem. And I want the domain, base 10, of the square root of 1 minus x. Now because it's a square root and we want to keep what's under the square root positive, then we have 1 minus x has to stay greater than 0. Or negative x has to stay greater than negative 1. X is less than 1. So we have from negative infinity to 1 as the domain. So here the domain, what you can put in for x can be from negative infinity to infinity. You can put in any exponent there that you're raising a to, but what you're getting out for the range is from 0 to infinity in exponential form. In logarithmic form, your x value, the answer that you can get, is from 0 to infinity. The log has to stay greater than 0. The range, here what you can get out for an answer is from negative infinity to infinity. These are the opposite of each other. Okay, so we have this problem, and the answer that we get when we raise 2 to some power is x plus 1 over x minus 3. And so what we want to keep that so that we have x plus 1 over x minus 3 greater than 0. Now, x has to be greater than negative 1 in the numerator. But we know that x cannot equal 3 in the denominator. So the domain, what you can put in, is from negative 1 to 3 or from 3 to infinity. So we know we have to stay greater than negative 1, but we know that we cannot include 3 because it would give you division by 0. So there's a couple of different things that you need to be looking at in the domain there. Okay, so just a little bit on natural logarithms. The natural logarithm, ln e is equal to 1. ln of 1 is equal to 0. So when you see ln x, then that is the same as the log base e of x. So when we have y equals ln of x, so we have x is greater than 0 if and only if x is equal to e to the x. So it's just another way of expressing this. This is natural logarithms. So when you see ln of e to the x, that is equal to x, as long as x is a real number. Or e to the ln x power is equal to x, and again, x has to stay greater than 0, as we talked about with the domain.